Topics in post-harvest technology. Pre-cooling and half-cooling time. Pre-cooling is the rapid removal of heat from a commodity before it is placed in storage or before it is shipped. Pre-cooling helps to maximize shelf life by rapidly reducing a product's respiration rate and its rate of water loss. Pre-cooling reduces the refrigeration requirements in storage and during the transportation of produce. There are 5 pre-cooling methods: contact icing, forced air cooling, hydrocooling, vacuum cooling, and hydrovac cooling. The rate of cooling varies depending on the commodity pre-cooling method combination, and differences in cooling rate are measured as half cooling time. The half cooling time is defined as the time required to reduce the temperature difference between a commodity and its coolant by 1/2. Note, the larger the difference in temperature between a coolant and a commodity, the faster heat is transferred. However, as the commodity cools, the difference in temperature is less, so the rate of heat transfer slows. The net effect is that the half cooling time is a constant. It remains the same during the cooling process for each commodity pre-cooling combination. In this figure, we see a cooling curve for a commodity that has been picked from the field at 80 degrees Fahrenheit and for which we know the half cooling time is 10 minutes. The cooling medium is a coolant at 32 degrees Fahrenheit. Since by definition, the half cooling time is the time it takes to reduce the temperature of the commodity being cooled from 80 to 32 degrees Fahrenheit by 1/2, 80 minus 32 is 48, and half of that is 24. So 80 minus 24 is 56, and when we measure the temperature of the commodity after 10 minutes, we will find that the temperature of the commodity is 56 degrees Fahrenheit. What happens after another 10 minutes have elapsed? Well, again, by definition, the half cooling time is the time it takes to reduce the temperature of the commodity being cooled by 1/2. So we're starting at 56 degrees Fahrenheit, and the coolant is 32 degrees Fahrenheit. 56 minus 32 is 24, and half of that is 12. Subtract 12 from 56, and we're going to find that after 20 minutes of cooling, the temperature of the commodity is going to be 44 degrees Fahrenheit. What about after 30 minutes of cooling? That's another 10 minutes, which is another half cooling time. Well, 44 minus 32 is 12. Half of that is 6 degrees. We subtract 6 from 44, and we will find that after 30 minutes of cooling, the temperature of the commodity will be 38 degrees Fahrenheit. Since the rate of heat transfer slows during cooling, cooling becomes an increasingly inefficient process. Therefore, industry practices to cool for 3 half cooling times, which removes 7/8 of the desired heat from each commodity. Once pre-cooled, the commodity is then placed into simple refrigerated storage, which then works to bring the product's temperature down to the final desired level. By pre-cooling and quickly removing 7/8 of a commodity's field heat, the respiration rate of the commodity will be greatly reduced, as well as its tendency to lose water. By pre-cooling, a commodity's shelf life is very quickly and dramatically increased. The half cooling time is unique for each commodity cooling method combination. As such, half cooling time depends on a number of factors. The first is the accessibility of the product to the cooling medium, and that's going to be affected by how the product is packed in a container, whether it's loosely or tightly packed. The venting of the container also affects the half cooling time, and venting refers to the number of vents or holes in each container, the size of these holes, and the placement of the holes on each container. The half cooling time is also affected by the velocity of the coolant going over and through the containers, the type of cooling medium, and the commodity itself. In this figure, we're observing cooling and reheating curves for large and small potatoes. The red line represents small potatoes that were cooled with cold water at 32 degrees Fahrenheit. Internally, the small potatoes started at about 65 degrees Fahrenheit, and you can see that within 10 minutes, they dropped dramatically in temperature. Compare those results to the blue line, which indicates the changes in internal temperature of large potatoes that were also hydrocooled. Due to volume effects, the large potatoes take much longer to cool, and you can see that they cooled at a much slower rate than the small potatoes. Now, what happens if you take the cold potatoes and then reheat them? In this test, they were placed in a chamber set to 104 degrees Fahrenheit. The purple line represents the reheating curve for small potatoes, and you can see that they reheated very, very quickly. As before, since the large potatoes cooled slowly, they also reheated more slowly than the small potatoes, and their reheating curve is represented by the green line. Since the half cooling time is a constant, it can be mathematically represented. To calculate the half cooling time for any commodity coolant combination, use the following formula. This formula, H is the half cooling time. We have a factor 0.301. T represents the time we're observing cooling, that is the length of the test. In the denominator, we have log base 10. There are absolute value bars, and within them is S minus M over F minus M. S is the starting temperature of the commodity, and M is the cooling medium temperature. F is the temperature of the commodity at the end of the test. Again, M would be the cooling medium temperature. Here's an example problem. Cauliflower is being cooled using air with a temperature of 35 degrees Fahrenheit. The cauliflower is initially 65 degrees Fahrenheit. After 15 minutes of cooling, the cauliflower is cooled to 63 degrees Fahrenheit. What is the half cooling time for this commodity cooling medium combination? Again, here is our formula. Here, we've plugged in the relevant numbers. 15 represents the 15 minutes that we cooled the cauliflower. The 65 in the denominator is the initial temperature of the cauliflower. The 35 is the temperature of the air, our coolant. The 63 is the temperature of the cauliflower after 15 minutes of cooling. We solved this formula and determined that our half cooling time is 150 minutes or 2.5 hours. 2.5 hours is a very slow half cooling time. Ways to decrease the half cooling time for this cauliflower air combination, that is, ways to increase the efficiency of the cooling process, would be to increase the velocity of the air and to ensure that there are sufficient well-placed vents on the containers. Summary points. Precooling is the rapid removal of product heat before storage or transport. Precooling is necessary for many commodities to maximize their shelf life. There are 5 precooling methods, and differences in cooling efficiency may be compared using half cooling times. The half cooling time is defined as the time required to reduce the temperature difference between the commodity and the coolant by 1/2. Half cooling times are unique for each commodity cooling combination and are a constant during the cooling process. Half cooling times depend on the commodity, cooling medium, the velocity of the coolant, and the accessibility of the coolant to the commodity. Since the half cooling time is a constant, it can be mathematically represented and predicted.